If you're following along with the orbital diagrams and electron configurations kind of series of videos I'm doing here, we last left off talking about the Aufbau principle. And if you didn't see that, then this is the Aufbau principle, which is a way for us to figure out the order of the energies going from lowest to highest of our orbitals and our different orbital types. And what we're ultimately going to do is to relate this to the periodic table. But this gives kind of a handy memorization tool that we can use to figure out that order of energies. And so the way that you'd interpret this is that, this is your increasing order, 1s, 2s, 2p, 3s, 3p, 4s, and we're kind of going up the different columns here of this grid that we've created. So let's relate this back to an element. Let's look at calcium. So if we look at calcium on the periodic table, we see that it's number 20 here. So it's in period 4, group 2. That means that it's an alkaline earth metal. Period 4 here includes all the way across. This is the first period on the periodic table where we have kind of these two sides of the periodic table joined by our transition metals here. So calcium has 20 protons. We can tell that from our atomic number. And in a neutral atom of calcium, then, we have 20 electrons. And again, we as chemists are interested in the electrons and where the electrons are, energetically speaking, as well as physically on an atom, because that gives us information about the type of chemistry that it's going to do. So if I'm going to fill in 20 electrons to my orbital diagram here, which I've created, again, using the Aufbau principle, so 1s, 2s, 2p, 3s, 3p, 4s, 3d, right, which was kind of a weird thing. We had been going numerically, but this 3D is kind of a weird one. We'll talk about why that is a little bit later on. Now, electrons like to be at the lowest energy possible, so we'll start at the bottom, and we can fill in 2 in our 1s. Each of these lines that indicates an orbital type can hold up to 2. 2 in my 2s. I'm going to follow Hund's rule here. So 4, 5, 6, 7, 8, 9, 10. So I've used half, so I need to account for the other 10 electrons. So here's 2 more. One spin up, one spin down. And then in my 3p, here's 6 more. So now I've accounted for 2, 4, 6, 8, 10, 12, 14, 16, 18. I need 2 more, which I can fit into my 4s here. Now, if I wanted to translate this into an electron configuration, which is just another way to express this same type of information, I can express either kind of visually where the electrons are located. And again, this sort of makes us think of the Bohr model of the atom, where we have our nucleus at the center. We have our bullseye of shells around. Oh man, not a geometry major. Woo. Okay, so if this is n equals 1, n equals 2, n equals 3, and I'll need a 4th shell too. So let's make a gigantic one. Let's just do it. I do what I want. Okay, here's n equals 4. All right, so I'll put 2 in my 1, and then I have 8 total in my 2nd shell. So it's an n equals 2, n again being that principal quantum number, which tells me the energy of the electrons relative to the nucleus. I have 8 in my 3rd shell. And if you've seen models of the atom, you've probably seen as you're kind of building these up what the potential is for all of these different electron types. And then I have 2 in my 4th shell. So we'd say then that the highest energy electrons are in the 4th shell, and there's 2 of them. So we're kind of, this is the picture that we have. This picture of the atom has this visual representation in this orbital diagram. And we can translate this all into kind of a more succinct symbolic version with our electron configurations. So they're all interconnected and they're all telling you the same types of information. So those 20 electrons on calcium can be also represented by interpreting my symbols here. So I'm going to say in the 1s orbital, I have 2 electrons. That's what my superscript tells me. 2 electrons in the 1s. In my 2s orbital, I also have 2 electrons. 2s2 is the way that we'd read that. In my 2p orbitals, so again, I'm kind of listing them out in order from lowest to highest. In my 2p, I have 2, 4, 6, so I have 6 as a superscript. In my 3s, I have 2. In my 3p, which comes next, so again, I'm just kind of reading up my energy here, I have 6, and in my 4s, I have 2. So the way I would read this electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And this is the electron configuration for calcium. And I know that because if I add up all of the superscripts, which told me how many electrons are in each of these orbital types, then that will tell me how many electrons I have total. So that would give me 2, 4, 6, that's 10, 12, 18, 20. So calcium with my 20 electrons. So a neutral atom of calcium. All right. So if you have these symbols, then if I give you an electron configuration, you should be able to tell me then what element in its neutral state that it corresponds to. So if I said that we had, for example, 1s2, 2s2, and I said, whose electron configuration is this? Then this is a little bit of a trick question, but if you were thinking about a neutral atom, then you would say, well, there's 4 electrons. And so if I go to my periodic table, then I need to find number 4 in the periodic table, which tells me that there are 4 protons, which means if I have 4 electrons, this must be beryllium. Okay, so if you have an electron configuration, you can figure out the neutral atom it corresponds to, and vice versa. Then using the Aufbau principle, then we can figure out the order of these different orbitals and in terms of their energy, and then we can fill in the electrons based on how many different types there are. Again, S has 1, P has 3, D has 5, and F has 7. Okay. Now, kind of the cool thing about this, the cool thing about all of the things in chemistry, is that this can all be related to the periodic table. And so if we think about where beryllium is, again, I'll bring my periodic table here. If we think about where beryllium is on the periodic table, it's in the second period, so the second row. It's in the same group as calcium, right? So it's in those alkaline earth metals. And so if we look at beryllium and calcium, which are the 2 examples that I used here, what they have in common is they both end with electrons, 2 of them in fact, in s orbitals. And so the highest energy electrons for each of these are in s orbitals, and they're filled, and they both happen to be in the same column. And we know about the periodic table that there's these patterns that follow. And so based on where an element is on the periodic table, I can tell you what the highest energy electrons are going to be for that particular element, which is just dang cool. So if I draw a little schematic of the periodic table, which as you've already seen, drawing is definitely my forte, but I have done this a time or 2. All right, so here's kind of my schematic of the periodic table. We have the first 2 columns here. So our alkali metals, our alkaline earth metals, here's our transition metals, and then we have our 6 columns here at the end. This is groups 13 through 18, or 3A through 8A, depending on whether or not you're using your A's and B's categorization, or if you're just numbering straight across. We know that there's 18 columns across on the periodic table. And then the inner transition metals, which are here, these are our lanthanides and our actinides, is this little island that actually fits in right here if I was to stick it in where it belongs in the periodic table. So it would stick in there, but what we found is that it really has more in common with itself than it does with the rest of the periodic table. So it's easier to just kind of take it out, condense things in a little bit. Now what we found then is based on where the elements fall in these different blocks, because there's really these 4 distinct sections of the periodic table, then we can determine the energy of its highest energy electrons. And the highest energy electrons are called valence electrons. So highest energy meaning in the outermost shell. So thinking about the Bohr model of the atom, all of the electrons that are in the outermost shell that is occupied are going to be the valence electrons. For the main group representative elements, which are my groups 1 and 2, kind of the main group elements that are on this side of my metalloids, on this side of the periodic table, then the valence electrons are the highest energy S and P electrons. And we'll relate all of that to the periodic table here in just a second. But the cool thing is, if I have anything in these 2 columns, they are what's in the S block. And if we have anything in our transition metals, this is in the D block of the periodic table. Anything here in our main group, and then kind of the extended, the post-transition metals, and the metalloids and the non-metals that are over here, these are in my P block. And then this floating island of lanthanides and actinides, these inner transition metals, are in the F block. So what this means is that the highest energy valence electrons are in these orbital types for the elements that are in this particular part of the periodic table. So again, with beryllium, we said beryllium is in column 2, as was calcium. So these highest energy electrons for them are in the s orbitals, and they fall in the s block. This is also true for sodium, for example, and potassium, and anything that falls in our alkali or alkaline earth metals. Okay, so let's look at another example. If we wanted to look at chlorine, say, give myself a little more space here. So chlorine is over here in the halogens column. It's in group 17 or 7A. So because it's in the halogens column, and this whole block of elements is in the P block here, chlorine has 17 protons. That's its atomic number. And it has 17 electrons. Because it's over here in the P block, like we said, those highest energy electrons are going to include P electrons. That's going to be what the electron configuration for chlorine ends with. And when I look at it, then it actually is 1s2, 2s2, 2p6. So now I'm full up through these p orbitals, right? If we're picturing our orbital diagram here. So 2 in my 1s, 2 in my 2s, 6 in my 2p. Then I have 3s2, so that gets me to 12. And then now I need to account for 5 more, which are going to be in my 3p. So 1s2, 2s2, 2p6, 3s2, 3p5, and if I add all of my superscripts up here, 2, 4, 10, 12, 15, 17. So that's my 17 electrons here. All right, and these p and s, these highest energy s and p, give me my valence electrons of my chlorine. All right, now I want to talk a little bit more about this, but I'm going to do this in part 3 of the video. Now that we know where the blocks are in the periodic table, now I want to talk about how we can figure this part out, the electron configuration, based on its location. Because instead of figuring out and using the Aufbau principle and remembering which ones are the highest energies and how many electrons I have, I can actually just count over using the periodic table. That's how powerful it is. And there are some versions of the periodic table that actually have the electron configurations built into the information that they give. They are that dang important. Okay, so if you're interested in more information on that, then check out part 3, and I will see you there.